Hey folks, welcome back. We are here at Channel 9 Live with esteemed colleague Alex Turner.
Yes.
Alex, what would you say you do for Microsoft?
What do I do here? I work on the Managed Languages team, so I'm a program manager for the Managed Languages team, and we kind of changed the name of our team just about every release. We used to be sort of Visual Studio languages, VB C# languages. What we do is really the compilers and all the things that sit around the compilers. So the language services, all that stuff that kind of powers final references and go to definition, all those kind of things inside VS.
Cool, cool. And we are taking questions, so whether we can ask you all sorts of questions, right? So.
Yep.
Let them go.
Yeah.
Send them, of course, as we're going. Async, of course, is one of the big topics.
It is.
And you actually had, how many sessions did you have?
I had 3 sessions this time on Async here at TechEd.
All right. So what were the sessions? Kind of what are the big things that you were talking about?
So one of them was really around async in Windows runtime, and so we really in the VS 2012 release we did really 2 core things as the language teams. We did support for the Windows runtime. So you could write Windows Store apps. We also did support for async and all the new stuff we have around the await keyword. Really helping you kind of call into those asynchronous APIs, the ones that are really prevalent everywhere, including in the Windows runtime that are kind of popping up.
So, taking a step back, and maybe some folks haven't programmed with async and await, maybe just because they haven't built their first, say, Windows Store application. Sure. Why async await? Why is it needed?
Right. Well, what we found, like if you actually look in environments where you really want kind of like either on the client you want responsive apps or on the server you want kind of those extreme high scalable servers, you really need something where you're not going to kind of block the threads that you're on, right? So if you're on a client app, you're writing to the UI thread, you want to go read from a disk, you want to go read from the network, right? You could spin up a thread and block on that, but then you have to go marshal back to the UI thread, your code starts to look funky as you're bouncing back and forth. What you really want to do is kind of sit there and say, hey, I want to pull in some data, I want to do it there on the UI thread, but you don't want to block that thread. So, there's been APIs that have been around forever. You think of like, begin read and end read from way back in the day, and there's, web client, which has asynchronous download methods, but you always had to kind of specify this callback, this lambda that you're going to put into that to say, all right, well, after you're done downloading, here's what you do.
This is the download completed event is going to fire, and then you actually have your data.
Exactly, right? And so, once you have that, that's fine if you're going to do one download. Okay, download this, when I'm done, put it into the UI. But when I take that, maybe it's giving me some XML, I parse it, I get a URL, I go fetch something else, or maybe I have one of 3 paths that could go down, or I want to do 10 of these in a loop or something. Mm-hmm. All these kind of things start to get a lot more complicated than they have to be. Let's say I want to do something in a while loop. Well, if I'm in the middle of a while loop and I want to kick off an asynchronous network download, what do I pass as kind of like the rest of what I'm doing? It'd have to be like the rest of that while block that I'm in and kind of like all the future iterations of the while and the stuff after it, and your code kind of gets all flattened and rotated and weird. And so you don't really want to do that. And people end up having all these kind of chained nuggets of functionality. Like my favorite analogy, people talk about spaghetti code when you have go-tos and it messes everything up. What I've heard for people talking about async, when you have these like nuggets that are talking to each other, you get macaroni code. These nuggets that are, each one is doing a little bit of your logic, right? And you're bouncing between them. And when you look at one, it makes sense. But when you look at like 10 or 20 or 30 that you have, it's hard to reason about your app anymore because it's been so scattered about.
Yeah, and these are specifically new keywords. Yeah. And what platforms are they on? Because Windows Phone 8, we had a session earlier, and Windows Phone 8 now supports it. Windows Store, and have you all backported to any other programming languages or platforms?
Well, so we came out, we had .NET 4.5, right? What you can actually get if you're not using .NET 4.5 yet, if you're using .NET 4, if you're using like Silverlight 5, we have something called the Async Targeting Pack. We actually have a new version now. You go search on NuGet, it's like I think called Microsoft.bcl.async. You can go find that package on NuGet, and that'll let you actually sort of get started doing this stuff, right? You can talk to asynchronous APIs. We have some helper APIs that are in there that are built in, and you can actually start going and awaiting these things in your kind of linear flow, right? Because that's really the benefit, right? Like, in that before case, you have all that macaroni code, things bouncing between. The goal, once you actually start using async and await, and you're talking to these APIs on whatever platform, is that you can really just write your code linearly again, the way you did back when you used synchronous stuff before you really cared about all the responsiveness.
Sure, and of course, feel free to send us questions as we go through. Yep. So, while you're writing code, there's probably 2 different scenarios where one is, I'd call the fire and forget scenario. Yep. Like, I just do this thing, maybe just send a ping to some server or something. Right. And then there's the, hey, I want to be able to do this and give me some way to coordinate. And within those two scenarios, there's always the other part, which is I want to be able to do things like cancel that specific task. So what are, like, and maybe that's then 3 different scenarios, but what's the fire and forget scenario? Is it just, because then you're actually handling a task as opposed to using these async and await keywords, because you don't really want to await, right?
Well, that's the thing. So like, you think of something like a button click handler. So you're going to be on a UI thread, someone clicks a button, you're being called by the message pump that's powering the UI, and you're going to get into your code, and the message pump doesn't really care when you're done handling that click event. It's going to just, when it gets control, go spawn something else, even if you're still kind of asynchronously processing other stuff, waiting for results and changing things in the UI. And so those methods that you write that are event handlers, you mark them as async void methods, right? Because the return's void, nobody can track your operation as it's ongoing. It just represents something that you get kicked off by the message pump, and you can go on and do asynchronous operations. You can await things in there. If you're writing helper functions, though, let's say you write some function that's going to go query 5 databases and pull results back, munge them, and then return some aggregated result. You obviously need to wait until you do all that work and calculate the result before you go on. So when you write those kind of methods, you do care about waiting for it to complete. It's not fire and forget. Right. It's a method you want to track, and track not just completion, but also what result it comes out with, or an exception if it fails. And so those are the methods that aren't going to return async void. They return async task, or async task of t, if you have a result. And when you await one of those methods, you can actually await it because you have this awaitable task object you get back. And the act of awaiting it kind of pauses your method. And then when it finally comes back, if there's a task of t, if it's got like that t result, it comes back out, and you can assign it to a variable. And that's how you can pull data out, just like you were calling a synchronous method. It's that easy.
And in that case, it's actually, it looks like the next line of code that would execute is the one after the awaited
Exactly right.
code.
You're not making a bunch of lambdas. You're not kind of splitting your code up into pieces, right? You just have basically one method that represents that linear workflow that you want to do.
And so let's talk about like a cancellation. Like, what are some of the right ways to handle cancellation? Because cancellation can be kind of tricky, especially if you're talking about, one is just sort of the simple way, but nested and all the different scenarios there. Like, what actually happens?
So cancellation is one of those tricky things. It sounds pretty simple. It's like, oh, okay, well, if someone clicks a cancel button, we're just going to go say cancel the download. And if you have one thing going on, it can be. But imagine something, right, where I have this kind of linear flow, and maybe I'm starting off and I'm downloading one thing, and then I'm going to go calculate what to do next, and I download that. If the user clicks the cancel button, maybe one of 5 different things is going on, right? And one of those things might be one of these kind of helper methods that I called, and inside there it's going to have other things it might be doing. So if I wanted to do that manually, I'd have to keep track of what kind of thing is active at the moment, and then remember, oh, is this active, is that active? Do all this bookkeeping to figure out what to cancel. Right. So the mechanism we have to abstract over all that is this idea of a cancellation token. Okay. And so you have an API that supports cancellation, and instead of having like a separate cancel method, when you call the API, it takes a cancellation token. And so I would call my download method and kind of pass it a token, right? And pass that same token to all the other downloads I do, and all those helper methods that are going to pass that token on to their things that they want to cancel. And so the idea then is, when I want to cancel, I just trigger cancellation on that token, and whatever thing happens to be active that's currently holding that token, whether it's a download or some file I/O or something, that would then throw the cancellation exception and bubble up from there. And I don't have to do all that bookkeeping to remember what's active at the current time. But I do need
to, like, let's say you have your one function and that calls something else, then I need to pass in as a parameter?
Yeah.
Or does it automatically inherit the state objects?
Right.
Like,
well, so that's the thing. If you
enclosed variables, or if
well,
you will.
you do have to pass the parameter, but the idea then is that you do that only if you know that in that method you're going to be passing that token on to something else that you'd want to cancel, right? So assuming you are going to go hand things off and want a cancellation token to hand to your method's downloads, you would just decide to accept a cancellation token in as a parameter, sometimes like an optional parameter.
Okay, yeah, actually an optional parameter would be nice, just so that way you don't have the uglier signature, I guess. Yeah. Okay, cool. Now, so people have been using async and await for a while. We have announced it as far back as, what was it, PDC 2010, I think it was?
It was pretty far back. We had CTPs like really early, right? And it was pretty cool to get that feedback. We had one design originally, which was more around like async blocks, and we're asking, hey, what would this look like? If we had this, how do you feel? And people gave us good feedback. We had an early async CTP. People tried it out. And they told us where there were perf issues. We're able to figure out what we want to optimize and really squeeze that perf out so that you don't have to feel like, oh, am I choosing between kind of performance or convenience with the code I'm writing, and sort of all but the most extreme scenarios, it becomes really like a non-issue.
Yeah, actually, so are there any things where, from a performance perspective, that you do need to worry about?
So the only thing is if you find yourself doing like a whole lot of awaits per second, like if you were kind of awaiting like a really tight inner loop, like the kind of rule of guidance we have is like if you have like 1,000 or so awaits, even maybe up to like 10,000 awaits per second, the overhead from kind of the async machinery is going to be really negligible. Like you're probably going to have more overhead if you try to like fudge it yourself, right, or have issues with exceptions. Like we've optimized this even deep into the CLR with how we implement task to make this really streamlined. And so as long as you're getting something where you have a reasonable amount per second, you're good. The only catch is if you say, oh, I'm going to loop 1 million times a second and I'm going to wait like, read byte async or something. You make some helper method that gets 1 byte. Well, to get 1 byte, if you're going to do all this infrastructure around it, maybe then you start to pay the cost, right? Even, I think I did a demo today, right, and part of it was sort of analyzing this perf cost. And when we demoed it, it was about on my laptop, it's like 1/10 of a microsecond or something, which is that async overhead. So again, if you have 1,000 of those, it doesn't matter, right? If you have 10 million of those, maybe it does start to add up. And so it's just about being reasonable. The one piece of guidance we give is if you're writing an async helper method or an async library for somebody else, try to make it chunky rather than chatty, right? Something where you go and you say, I want to fetch like an entire kilobyte of data or something rather than kind of pulling one byte at a time. Yeah.
Sure. That's kind of sort of common sense anytime you're doing either network boundaries or anything else too.
Yep.
So speaking of which, best practices. You had a talk on best practices. And I think it's always interesting to hear not only just the best practices, but the please stop doing this.
Right.
You see code, you see people doing it, and they're, say, for example, doing async void where they shouldn't, as one example. Like what are some of the key things, like if you had to say, just don't do this?
Well, I mean, that's actually the one. I think I would actually, if I had to pick one tip, even one thing to kind of remember as you take away from this session or from this talk, just do not use async void everywhere just because it's there, right? Async void, as we talked about, is for specifically those fire and forget scenarios.
Right.
And often you don't actually have a fire and forget scenario, even if you think you do. So for example, you might not care about any particular result from this thing that you kick off, but maybe it's going to have an exception, right? And so unless you actually, in an async void method that you call, had like a try catch that caught like every exception, if something unexpected bubbled out and got to the top, that could actually try to surface out. But even if you put a try catch like around your call to that method, it's not going to be able to catch it because there's no await. There's no way to kind of pull that asynchronous exception out of the async method. So what you really want to do is one of two things. Either you have to put that try catch in there and make sure you're very careful to catch everything that could happen, or just make it an async task method and then make sure that where you call it, you await it so that those exceptions would bubble out there, and then you can have an outer try catch like you probably wanted to do outside.
Okay, yeah, that's certainly one. And the reason why is it really just performance, or is it just good taste, or what are, like, because people say, okay, well, I mean, my code's working. Do I really, outside of exception handling, are there things with performance, or is it?
Well, that's one of those things. Like what we see, like we kind of looked at the forums and saw where people are hitting issues, and one of the things you'll see is somebody who gets their app to work, right? And it'll kind of look like it works. It'll work when they test it, right?
It works on my machine.
It works on my machine. Works for me. Like not repro. And then you put it out in the wild, and somebody's running it, let's say, on their phone where their network is slower, or any kind of different condition changes. And when you have async void, what you're counting on then is that, well, this thing could take some amount of time, and then my original method is going to keep flowing because I'm not actually awaiting it. My calling method is not waiting till it's done. It's just going to keep going whenever it gets control back. So you can easily get race conditions. And race conditions are a great way to have something that kind of works sometimes when you test it and doesn't work other times when your customers are trying to actually use what you're doing. So our real guidance is saying if you have an event handler or some kind of really top-level thing that you're calling into, then that's an okay place for async void, and that's where it's recommended, which is why we have it, right? But if you're doing anything else, if you're writing any kind of helper method, you should really think pretty hard before you make an async void helper method, because you're probably better off with something that's task returning, so you can actually await it.
Okay, and you mentioned race conditions.
Yeah.
That's one of the things and the benefits of the whole async await is that it gives you a simpler syntax, so that, because people always said, oh, asynchronous programming is too hard, there's too many problems. Like, how does your team, or just building applications, find out about race conditions? What are the tools that you all use, whether it's in the CLR or especially when you're actually building async libraries, how important that is? What do you all use for that?
So one of those things, I mean, like, and again, there's different ways you could get race conditions. Like, it depends what kind of stuff you're doing, right? If you're doing a lot of I/O-based parallelism, like stuff where you're just kind of pulling data in from the network, but you're not really doing that crunching on your own box, really a key way to prevent race conditions is to make sure that you're always doing those things where you're awaiting, right? Where I'm making sure that I'm pulling back tasks, I'm calling these task returning APIs. because then I can actually easily coordinate. Like if I have a flow inside an async method that I'm writing, I can easily make sure that nothing is kind of proceeding faster than I expect it to if I have that kind of simple flow. But people do more complex things than that, right? Especially if I'm doing CPU-bound work and I'm trying to coordinate a bunch of tasks that are doing complicated things. Those tasks might have interesting relationships to each other. So again, one key way, even for CPU-bound work, is to try to hook up these relationships. So it's like, well, if one of these tasks I'm kicking off can do a bunch of work, but then at some point it depends on the result of some other task that's in flight. Don't just kind of like set some variable and kind of hope that this one's going to be there in time. You can take advantage of the fact that we have that task type that's kind of shared between all the network download IO type asynchrony and also the CPU bound, the task asynchrony people have been doing with the TPL, the task parallel library since .NET 4.0, and say, all right, well, this little bit operation I'm going to do over on one core, I'm going to represent that as an async method, even though it's doing CPU bound work. And when it finishes, it's going to return for its task and say, here's my integer result value, right? And then my other bit of work could just decide to await that bit of work, right? Await the task that method has. And so it doesn't matter which one of these gets to that kind of like union point first. At the point when I need the value and I await it, now I'm going to kind of let go of my thread, right? And only come back when I actually have the data that I need. So taking a sort of stronger dependency on using await, using async, even for CPU-bound work to kind of coordinate between these different little chunks of work you're doing rather than hoping that you get something into a data structure in time for someone else to pull it out. That's kind of a good way to avoid those race conditions in the first place.
Yeah, but when they happen, in production, we don't know why it's happening, or it's happening on this processor and not another one. Like what are the things that you can just walk up to, something running in the CLR, like are there...
One of those good things when you do have one of these kind of wacky situations, you can't figure it out. We can do profiling, right? And you can do that kind of profiling to figure out perf issues, but there's also the concurrency visualization when you're doing profiling. And you can start to tell, well, is this thread blocked, or did I expect this thread to be blocked when it's actually going on?
We'll talk about concurrency visualization. Assume people aren't familiar with that.
Yeah. And so what you can do is it's sort of you go into the profiler as if you want to do, you go to like the analyze menu as if you want to do just kind of like regular performance profiling. And then I forget the exact menu item. I think you say you want to make a new analysis session. And then you can choose what kind of analysis you want to do. And one of them is concurrency analyzer. And you enable that, and then what you're able to do is just kind of run your app, and you go through a scenario, perhaps a scenario that's kind of behaving not the way it should, or you're having deadlocks or race conditions. Deadlocks are another case where you can basically have, I have one thread, and then maybe especially a UI thread, it can be bad, then something on the UI thread is kind of waiting for something else, and I'm stuck, and my app freezes, right? And I want to figure out why those race conditions or deadlocks are happening. You do the concurrency visualizer, and you can see all those interrelationships between the threads you have and the tasks you have. One other thing you can do besides that kind of visualization is also just pause your app. If there's something weird going on in your app that's related to threading or related to these tasks that are in flight, you pause the app and then you take a look and you say, all right, well, here's the tasks that are active right now, and I can see what their stacks are, right, for all the tasks that are running.
Inside the concurrency visualizer.
Well, inside the concurrency visualizer, you can see all the different things that are running, but even outside, even if you haven't visualized, even if you're just broken in the editor and like you've noticed an issue or you hit an exception.
Oh, I see. Okay,
right,
you're debugging.
You're debugging no matter where you are. You can just go and you can pull down this kind of parallel tasks view, and it's going to show you all those active tasks that are there. And there's kind of...
what is the parallel tasks view? Is that just a debugger window?
It's a debugger window that's in VS, and it shows you kind of a list of those active tasks that the task parallel library is tracking. And among those tasks, like each one of them is going to be in the middle of something or have some stack that is kind of waiting on at that time, if it's waiting for some CPU work that it's done, or it's kind of paused, waiting for some IO thing to come back. One of the cool things you can do then, next to the parallel tasks window, when you pull down kind of like the debug windows, and you want to see that, one of them is the parallel stacks window, which gives you this cool graphical visualization. And so the idea is, well, I might expect that right now I'm doing some bunch of distributed work that I've sent out. And I have a bunch of things that are all distributed, and maybe they're awaiting each other. And I expect that most of my work is going to be down some certain code path, some certain stack. But I want to verify that. So if I kind of pause my app and I look at the parallel stacks view, it says here's like the 100 threads that I have that are each kind of doing some work. And it unifies them. So it says, okay, well, 80 of them have this kind of common thing at the head, right? And then like 20 of them go this way and 60 of them go that way. And I can see, hey, where am I kind of spending my time right now? And where are things stuck?
I actually haven't used it, so I will have to...
It's pretty cool.
I'm going to have to write some gnarly code.
Yes.
And then actually
get yourself stuck so you can dig out,
Yeah, it's one of those things. This is how we learn. We write horrible code and then have Visual Studio tell us exactly what's happening. That's definitely cool. I'll have to play with that. And you mentioned the TPL. So for people that aren't familiar with that, those are things like parallel for and parallel for each. How do those kind of interrelate, or are there any issues or guidance that you provide for people to be able to use those? Because when people think of async await, they automatically assume threading. This is everything kind of threading and related to GPU.
Yeah, so
and
I mean,
CPU as well.
Yeah, like when you're using the task parallel library, came out in .NET 4.0. The original purpose of it was to do this kind of CPU parallelism and coordinate across all different threads that are doing a bunch of CPU-bound work.
Right.
And the idea of actually pulling that in was that you had this common way that you could reason about the different tasks that you have. And the TPL. You brought up parallel.for, parallel.for each. These are great ways, and these were ways that came out in .NET 4.0 about kicking off a bunch of work in a very simple way. So you imagine you have a for loop that you've written in it. You just kind of say, for I equals 1 to 100, go do this block of code. Well, let's say I want to kick that off on a bunch of threads. I could spin up a bunch of things and figure out how many threads I should have, or spin up a bunch of work items. But I can, in almost the same syntax I do just a regular for loop, call parallel.for. And I can pass it a lambda that would be that body
I think it's just an action.
Basically, yeah. And I can just say, all right, so start at 1, end at 100, and execute this block of code. And it's smart. It knows what's going on generally in your system. It knows optimally I should use this many threads to execute this because it's CPU-bound work and you have this many cores, so this is going to be the best way to do it. And you can kind of delegate all of that responsibility for figuring out how best to do that to this infrastructure when you find, hey, it looks like all this stuff is kind of independent. I bet I could just do each of these slices of this for loop all in parallel.
Sweet, very sweet. Daniel Moth had done some stuff, and I was when we were talking about CPU on the C++ team to actually parallelize and use the GPU.
Right.
Have you looked at that stuff, or is there anything? Because he had actually done, I think, some samples that made it available for CLR types that you could actually use. You had that nice expensive graphics card.
Right.
Why not parallelize there? Have you looked at that at all?
I haven't personally dug too much into that in terms of what you could do with the CLR, but I mean, it is a really cool thing because, like, when you talk about parallel stuff, even like what people are doing now, like you're mining bitcoins and stuff, right? Right, and people will do that on a CPU, and then all of a sudden someone comes out with a GPU algorithm for doing that, like to actually use shaders on a GPU to figure it out, and all of a sudden you're mining at like 100 times a faster rate, right? And people do these kind of things because we have this sort of super parallel system inside our computer that's really designed for graphics, but you can bend that to do all sorts of general purpose computation.
Right.
And we're finding more actual sort of data computation uses for that. Like C++ AMP is kind of one way people are digging into that stuff.
C++ AMP is what I was looking for, yeah.
And so right now that's kind of the primary way that people are looking into it, but like as the GPUs kind of keep getting more and more powerful and people figure that out, that's kind of where Moore's law is still kind of kicking butt, right?
Yeah.
Like, on CPUs, we have to sort of transition from this idea of, oh, we have one core, now we're thinking of 2 and 4 and 8, and we have to start thinking about how do we really ensure we're multi-core and multi-threaded.
Right.
But, in the GPU world, people have been thinking about doing parallel vector operations forever. That's like the whole point. And so those just keep getting better and better and better, and so that's just going to be more awesome over time.
All right, I'll have to look for more stuff on hacking the GPU. Just 'cause there's so much processing power, and it's things I think people would want to take advantage of.
Yeah.
One of the things that when people started to look at WinRT, how do you make the distinction between, you mentioned CLR types and WinRT types, right? Because they there's obviously some contextual boundary.
Yeah.
And async is a feature of Windows, right? It is whether you're using JavaScript with JavaScript promises, and so there's got to be some foundation such that common type can be able to use async across those different languages. Like, how does that all kind of work together? Or what are some of the types and how it's all kind of structured?
Right. And so when you're doing just pure kind of .NET async, right, or whatever, like obviously, ultimately, let's say you're going to do an asynchronous network download, there has to, at the very bottom level, be some sort of core, OS operation that's going to let you do that kind of async thing, and that's exposed through .NET APIs. So if you're using just .NET APIs, you can kind of go all the way up from there. When you're using Windows Runtime, though, Windows Runtime, because it has to run in JavaScript, where you're just running on the UI thread. That's what you're doing, right? There's a heavy dependence there on asynchronous APIs, even for CPU-bound work. Like you imagine image resizing. They have image resizing APIs, and they'll expose them in that way as an asynchronous API. So JavaScript can sort of automatically kick that off in a background thread when it wants to resize images. And so we have those APIs exposed on the Windows Runtime side. And just like with Task and Task of T, which we have on .NET, we have iAsync Action. an async operation T. Those are the interfaces that Windows Runtime uses in their APIs. And what we did...
And are there any real differences between those two, or are they basically just mapping interface types?
Right. Well, when you had originally kind of like the Windows 8 developer preview way back, there were more differences, right? So one of the key differences was that on the .NET side, we had this thing called hot tasks, where the task, when you call an API and you get it back, you know that it's already running, right?
Okay.
What we originally had when you called a Windows Runtime API was you would get it back and it was a cold task, which meant that there was an explicit start method that you would call on that. And what we did is if you awaited the API, the result of that, we would start it for you, which got the 90% case. But if you wanted to do other things, if you wanted to kind of hold on to it and await it later, you had to remember to start it. And it was kind of a pain. And so one of the things we worked with Windows on was, hey, let's make sure that we have the same experience across the board. And so now we have hot tasks inside the Windows Runtime. And so when you call Windows Runtime API, you know that, hey, I'm getting back something that is already started. I don't have to worry about, did I start it, didn't I start it, did I already start it, so I can't await it again. You really have that experience kind of all paved over for you. One of the talks I gave here at TechEd was about how you consume these async APIs, the ones that are in the Windows Runtime. And part of that experience is how cool it is that in the same method, in my async method that I write in C# or VB, like I'm going through and saying, all right, await this .NET HTTP API, but then right under it I say, await this WinRT image resizing API. And we're able to do all of those in exactly the same way because we present that same abstraction to you inside C#, inside those async methods. You can just think of it as your same linear control flow, no matter what kind of APIs you're targeting there.
Yeah, and I think when you start obviously playing with Windows Store applications or WinRT and these APIs, you have to learn async and await programming. So it's not like, hey, there's this thing that you should maybe pick up. You want to open a file, it's an async call. You want to make a network call. And folks that have been building Windows Phone have probably seen this with some of their web clients.
Or Silverlight. Silverlight is much the same way, right? Because in Silverlight, you have to do all of your operations on that main UI thread, because the main UI thread in Silverlight is the browser's tab.
Right,
the thread for the browser tab. And you have to go through that thread if you're going to ask the browser to do a download in your behalf. And so you want to go to that thread, you want to do these downloads, but you want to do it in a way that doesn't block that thread because you're going to freeze the tab. And so Silverlight took that early bet on saying, okay, we're going to have async-only APIs, but we didn't have the await support yet in the language. So it was kind of, at the first, kind of annoying to kind of go through that if you were going to chain these things together. And so now by bringing that to Silverlight, by bringing that to Windows Runtime, we can take a bigger bet and drive async deeper into the platforms because we know it'll be easier to consume at the top level.
Yeah, I mean, it really is all over the platform. So, which is another cool thing, in that you have that power. And again, the simplicity of await is just kind of awesome.
It is.
So, just running out of time here, but real quick. So, give people the talks and your Twitter name, just so if they want to have the reference, the sessions will be online. But what are the talks?
So the talks, the first talk is that talk about async in Windows Runtime. So you want to search, you can just search for my name on Channel 9 for TechEd 2013.
There you go.
So you'll find one of my talks is on async in Windows Runtime. The other one is this talk on 3 essential tips for async. And so these core things, one of them was async void. The other ones you have to watch the talk if you want to find out. There you go.
A teaser.
A teaser. And the third one, the talk that I gave today, was around async libraries, right? So a lot of the stuff we've been talking about has been around, hey, how do I write asynchronous apps? And how do I handle Windows Runtime and WPF and those kind of apps? But here's a lot of the tips that we haven't shared so much yet around how do I go and write performant libraries that don't deadlock and don't do these various, pitfalls that you could fall into. How do I make an API that anyone can consume anywhere without tying people down?
And are you on Twitter?
Unfortunately, I'm not on Twitter. I'm on Twitter, but as a lurker. I don't post anything.
Oh, you're a lurker.
I'm a lurker on Twitter.
You are such a lurker.
Sneaky.
All right, well, Alex, this has been great. Alex Turner, definitely check out his sessions. And thank you all for watching. Thanks.